Hi. Now in today's video lecture we will look into electrophilic substitution reactions in HaloArenes. Electrophilic substitution reactions we are already aware of what they are. We have already studied this in mechanism of organic reactions. So these are reactions where a weaker electrophile would be replaced by a stronger electrophile. Right? For example, if you look at these are electrophilic substitution reactions. We'll just understand the mechanism behind these reactions, right? Before you study these reactions, you should understand what all things are taking place in these reactions. So if you look at the first reaction, right, and if you remember electrophilic substitution reaction definition, I said where a weaker electrophile would be replaced by a stronger electrophile. Here weaker electrophile is hydrogen. Here also you have hydrogen, right? So here hydrogen, we know hydrogen is released as a proton, and proton is an electrophile, right? This is electron loving. It attacks at those sites that are electron rich, right? So here you have, in this reaction you have chloronium ion, which is a stronger electrophile. So this stronger electrophile will replace weaker electrophile proton from this position and this position. These are electrophilic substitution reactions, right? Now just again remembering what we have studied in the basic chapter of mechanism of reactions. Any organic reaction you talk about is a reaction between a substrate molecule, right? It's a reaction between, this you should remember for the entire organic chemistry. Substrate reacts with a reagent. Reagent can be an electrophile and a nucleophile. In this case we have it can be electrophile or a nucleophile. Electrophile is positive, nucleophile is negative, right? Positive, negative reagents, both these react to give you products. You should know this, right? Concept behind this. So substrate is an organic molecule, right? It's a hydrocarbon or a derivative of an hydrocarbon. Here we have HaloArene, right? Chlorobenzene as the substrate, right? And reagent is anhydrous ferric chloride, chlorine, right? Here the reagent is your HNO3 and H2SO4. Both these will react to form an electrophile, right? Reagent, which is nitronium ion. This is an electrophile, right? This electrophile will now replace a weaker proton, right? Weaker electrophile, right, from this position and this position, and will form this compound, right? Chloronitrobenzene. Similarly, here you have again a electrophile, right? Electrophile is this, and your reagent is concentrated sulfuric acid. Concentrated sulfuric acid will form this electrophile. Now this electrophile will again replace hydrogen atom, right, which is a weaker electrophile, from this position and this position, right, to form these two products, right? So now it is clear from these reactions. Similarly in Friedel-Crafts reaction, this is a very important reaction. Here you have, in this reaction you have CH3 plus as the electrophile. In this reaction you have CH3C double bond O as the electrophile, right? So these two electrophiles gonna replace hydrogen at this and this position, right? We call these two positions as ortho and para. We'll understand this in detail, why ortho and para products, right? So now it is clear what is an electrophilic substitution reactions, and how in all these reactions these reagents will form electrophiles, right? If you want to understand, this is a ferric chloride, right? Ferric chloride will cleave this chlorine molecule, right? ClCl, it will cleave this chlorine molecule and will form FeCl4 plus Cl minus plus. This is your electrophile, right? This is how these reagents will form electrophiles. Similar with other reactions where nitric acid and sulfuric acid will react to form nitronium ion, right? And this will attack the benzene ring, right? So a reaction is a reaction between a substrate molecule, a reagent, which will form your electrophile in these reactions, and a product, right? So all these three things are important to understand. Now in these reactions, just notice some of the things. Now in the product side, you see that we always have an ortho product and a para product, right? Ortho product, para product, ortho product, para product, right? So the common thing is in all these electrophilic substitution reactions, what we are getting is an ortho product, ortho and para products, right? And why we are getting this? Because of the directive influence of group which is already present in the benzene ring. Here we have chlorine, right? Here we have chlorine in all the reactants. So it is chlorine that will direct the incoming group, right? The incoming group is your electrophile. It will direct the electrophile at your ortho and your para positions, right? So this is important to understand the directive influence. This is due to ortho and para product is due to directive influence of already present group, right? Which is your chlorine in this case, halogen, right? So this halogen is ortho and para directing, right, in this case. And why it is ortho and para directing, we'll see that in a moment. Now the other important thing in these reactions is you will see that this ortho product is always minor, we have mentioned it as minor, and your para product is always major, right? So this para product would be in large quantity and your ortho product is in lesser quantity, right? So ortho would always be minor product and your para would be major product, right? The reason for this is that at ortho position, if you see the incoming group when takes up this ortho position, right, it will face hindrance, right, steric hindrance that we call as, with this Cl already present Cl group, right? So these will face kind of repulsion, right? And that is why minor product, it will be a minor product because this is unstable due to steric effects, due to steric hindrance, right? The electrophile when will occupy this ortho position, right, will face steric hindrance with the Cl group which is already present on the benzene ring, right, with this group, right? So due to steric effects or steric hindrance, right, it's kind of a traffic that we can say, that you can understand, right? Since you already have a Cl group present here, so when the incoming group will occupy this ortho position, right, it will face some kind of a steric, we call it as steric hindrance. It's kind of a traffic, right? So it will not take up this position, it will take up para position, because at para position you can see at para position the incoming electrophile when occupies para position is at a much distance, right, from the already present group Cl group, right? So it will not face any steric hindrance, right? That is why your para product is always in major quantity, right? So due to steric hindrance, ortho product, or let's write ortho isomer in the product side, ortho isomer is in minor quantity, right? And your para product would always be in major quantity because it is not facing any kind of steric hindrance, right? There is no steric hindrance, right? So these points are important, right, with respect to these reactions. Now we will see that why. We will understand the directive influence of already present group. We said that chlorine group, that the Cl group, halogen group, is ortho and para directing, right? We said Cl is ortho and para directing, right? And the other thing that you can see here is that we are using some kind of we are heating it, right? So the conditions of the reaction, right? So reaction conditions are drastic, right? You can see we are heating it, we are using concentrated acids, right? So heat is required here, right? So we have the conditions of the reaction would be drastic conditions. Why we are using drastic conditions, right? Drastic conditions for the these reactions, right? This is important to understand. First we will understand the directive influence, why we are getting ortho and para product, right? Why ortho and para isomer. If you look at, this is your chlorobenzene, right? Let me just rub this from here. So chlorobenzene we know has lone pair of electrons. It has lone pair of electrons. If you look at these structures, these are resonance forms of chlorobenzene, right? What happens is this lone pair of electron on chlorine will enter into conjugation with the pi electron system of benzene ring, right? We know that this pi electron system of benzene ring is a conjugated system, right? So what will happen is in chlorobenzene, this lone pair of electron on Cl will enter into conjugation with the benzene ring, right? So when it will enter into conjugation with benzene ring, it will move along with this delocalized pi electrons of benzene ring, thereby producing or making high electron density sites at ortho and para sites. These are ortho, these two are ortho sites, right? And this is your para site. So you can see that when electron will move along with the pi electrons of benzene ring, it is generating high electron density at your ortho position. You can see this is the ortho position, this is the para position, this is the ortho position. So at ortho and para position you have high electron density because of chlorine. Why? Because your chlorine, what it is doing is the lone pair of electron on chlorine will enter into conjugation with the benzene ring, right? Thereby generating high electron density at ortho and para positions, right? So your Cl, due to lone pair, right, will be ortho para directing, right? Lone pair will enter into conjugation with benzene ring, right? So it is easy to understand how this chlorine is ortho and para directing. Now we know that your benzene ring, your electrophile, any electrophile is a positive reagent, and we know that positive reagent will always attack at positive. Electrophiles means electron loving, right? Electron we know are negative, have a negative charge, right? So electrophiles which are positive reagents will attack at high electron density sites, right, which are in this case are ortho and para positions, right? That is why product that will get formed here is your ortho and para product, right? So this is your ortho and para directive influence of already present benzene ring, right? So this Cl group which is already present will decide what position would be taken up by the incoming electrophile, right? Because it has already created high electron densities at ortho and para sites, and we know that electrophiles will always attack at high electron density, which is ortho and para, right? In this case, that is why we get ortho and para. And why ortho in minor quantity? Because of steric hindrance, right? And there is no steric hindrance faced by para product, right? I hope this is clear, right? Now let's just look at one thing. Just if you look at this reaction, this is your chlorobenzene, right? When an electrophile will approach it, it will form a carbocation, right? It will form a carbocation like this, right? Like this, it will form a carbocation. E stands for electrophile, any electrophile in this case, this, right? This is a carbocation. Similarly, when an electrophile will attack a para position at this position, right, it will form again a carbocation like this, right? And we know that lone pair is in conjugation with the benzene ring, right? Here also, right? So this is what is getting formed is carbocation. This is a intermediate now, right? Now remember, right, this reaction goes through an intermediate, and we know that intermediate, these carbocations are highly reactive, right? Just keep remembering what we have learned in mechanism of reactions. So now this is your carbocation, right? Now we have understood one thing about the chlorine atom which is already present on benzene ring, which is its ortho and para effect, right? This effect where the lone pair of electrons on chlorine will enter into conjugation with the benzene ring, we call it as plus R effect, right? Plus this is a resonance effect, right? Due to resonance effect, your Cl is ortho and para directing. It has another effect which we call as minus I effect. Minus I effect. Due to minus I effect, what this benzene ring will do, it is minus I effect, we know, is electron withdrawing effect, right? So Cl, this already present group on the benzene ring, has minus I effect, due to which it will withdraw electron density from the benzene ring. So there are two opposing things, right? This due to plus R effect, right, which is due to the lone pair which is entering into conjugation with the benzene ring, right? It is increasing electron density at ortho and para site, and due to minus I effect, it is withdrawing electron density from the benzene ring, right? So now if you look these two effects with respect to carbocation, we know that carbocation are positive species, right? Anything that will disperse its positive charge will stabilize it, and anything that will increase its positive charge will destabilize it, right? So minus I effect is electron withdrawing, right? Due to minus I effect, this Cl will withdraw electrons from this benzene ring, right? When electrons would be withdrawn from the benzene ring, if you look at this carbocation, when electrons would be withdrawn from the benzene ring, positive charge is getting increased, right? When positive charge is increased, that means it is more reactive, or it is more susceptible to be attacked by the negative reagents, right? Or it is, just remember, since it is a carbocation, right, and minus I effect is increasing the positive charge due to electron withdrawing effect of Cl group, it will destabilize. Right, what it is basically doing is it will destabilize your carbocation, and your minus I, this plus R effect, resonance effect, will stabilize it, because due to this plus R effect your electron density or negative charge is increasing at ortho and para positions, right, which will when it will increase the negative charge, since it is increasing the negative charge on the benzene ring, that means it will lessen the positive charge of this carbocation, right. So it will stabilize this carbocation, it will stabilize the carbocation, right. So just understand these two effects of already present group, Cl group. Now what will happen is, this plus R effect, what it is basically doing is it is directing the incoming group at ortho and para positions, right. So your in chlorobenzene, right, orientation, right, the incoming groups are oriented at ortho and para position, right. So resonance effect in a way is controlling the orientation. It is controlling the orientation because it is directing the incoming group or orienting the incoming groups at ortho and para positions, right. Now we'll see what does this minus I effect will do. These two are opposing effect. Plus R effect is increasing negative charge, minus I effect is decreasing negative charge, right, because it is electron withdrawing, right. This withdraws electron from the benzene ring. So but among these two groups, minus I effect is more stronger, right. Minus I effect is stronger than plus R effect. Remember this, minus I effect is stronger than the plus R effect, due to which there is net deactivation, right. When we say the electrons are withdrawn from the benzene ring, that means deactivation of ring is taking place, right, because we know that this ring is activated, or this ring is negative because of it has a high electron density, right. So when any group present on the benzene ring will withdraw electron, that means it is deactivating the ring, right. So here minus I effect is deactivating the ring. So since minus I effect is greater than the plus R effect, so net effect would be that the ring will get deactivated, right. When we say ring will get deactivated, that means the electron density will reduce on the benzene ring, right. So since minus I effect is stronger than plus R effect, so there is net deactivation, right. There is due to this, let me just write it over here, there is net deactivation. There is net deactivation of benzene ring, right. Net deactivation means the negative charge will decrease, right. Negative charge due to minus I effect, which is stronger than plus R effect, right, will result into overall deactivation of the benzene ring. Now what will happen to these reactions? We know that the electrophiles here, these electrophiles are attacking these ortho and para positions, right, and these ortho and para positions, they are attacking at ortho and para positions because they have high electron density. Now what this minus I effect is doing, it is withdrawing electron, it is deactivating the ring, so it is lessening these negative charge on the benzene ring. When it will lessen the negative charge on the benzene ring, the attack of these positive reagents, right, electrophiles on the benzene ring will become difficult, right. So attack of electrophiles on this benzene ring will become difficult because of net deactivation due to minus I effect, right. Since ring is now less negative, more positive due to minus I effect, attack of these electrophiles would become difficult, right? When we say the attack of electrophile on this ring will become difficult, that means reaction will slow down, right? So further electrophilic substitution would be carried out only under drastic conditions, right? Further electrophilic substitution would be carried out only under drastic conditions because of the deactivating effect of your halogen atom. That is why we are using drastic conditions, right? So here this inductive effect, minus I effect, is controlling the reactivity. It is controlling the reactivity and it is making this ring less reactive towards electrophiles. That is why we are using drastic conditions to continue further electrophilic substitution of HaloArenes, right? I hope this is clear, right? This reaction is quite important, so understand it, right? I'll just quickly recap. This is a chlorobenzene which will undergo an electrophilic substitution reaction where the electrophiles generated by these reagents will attack benzene ring at ortho and para positions, right? Now we said that the already present group, which is Cl, is ortho and para directing, right? And ortho product will always be in the minor quantity and your para product would always be in the major quantity because of steric hindrance, right? Now the Cl group present, right, it has a lone pair of electrons. One of the lone pair of electrons will enter into conjugation with the pi electrons of the benzene ring, thereby increasing electron density at your ortho and para sites. You can see from these resonance forms, right? At ortho and para sites electron density is increased, right? So that is why we are getting ortho and para product, because your Cl group is ortho and para directing, right? That is, it is controlling the orientation. It is orienting or directing the incoming groups at ortho and para positions. Why? Because it has already increased the electron density at ortho and para positions, right? It has already increased the electron density at ortho and para positions due to its plus R effect, resonance effect, right? Because this lone pair has entered into resonance with the benzene ring, right? So due to which it is ortho and para directing. It is ortho and para directing, right? Now there is another opposing effect of this Cl group, which is minus I effect, due to which it will withdraw electron density from the benzene ring, right? When it will withdraw electron density from the benzene ring, what it is basically doing is it will destabilize your carbocation, which gets formed when this electrophile will attack this benzene ring, right? Now since electrons are getting withdrawn from the benzene ring, it is becoming more positive, right? And attack by the positive reagent will become difficult because positive will repel, right? So your reactivity would be controlled by the minus I effect of Cl, right? And that is why you have to use drastic conditions in order to further continue your electrophilic substitution reactions, right? I hope this is clear, right? So that is why we say minus I effect will control the reactivity of HaloArenes and your plus R effect will direct the orientation, that is the orientation of incoming groups, right? I hope this is clear, right? Just understand this substrate, reagent and product funda, right? And your why this is ortho and para directing Cl, right? And how the plus R effect will control the orientation and how the minus I effect will control the reactivity, right? I hope this is clear. Thanks.